This, which is our second talk in the Philosophical Issues in Space Science series that's being hosted by the Centre for the Humanities, Engaging Science and Society at the University of Durham. So our speaker today is James Schwartz. So James is based at Wichita State University. He is the author of The Ethics of Space Exploration, a collection, and a recent book with OUP called The Value of Science in Space Exploration, which I finished last week and greatly enjoyed, I must say. So James is going to talk to us today about planetary protection. Is life all that matters? Over to you, Jim.
Well, thank you so much for that introduction, Chris. I'm very happy to be here working. No, sorry, gotta click somewhere to get my. There we go. Okay. It's in Zoom, and this does not want to communicate with Zoom. It wants PowerPoint. So just wanted to start by thanking Chris, Peter, and Nicola for having me as part of this, and of course to Nancy for supporting this series in the chess program as well. And of course, to the rest of you in the audience, thanks so much for attending my talk. So I guess just a little bit of background about myself. I actually started philosophy kind of in philosophy of math, but pretty much for the last decade, my main focus has been on various issues related to space exploration from a number of different kind of philosophical orientations. And if I just had to pass on a single observation about philosophical scholarship related to space, what I'd say is that there are just so many possible vectors from philosophy into issues related to space. Virtually any subdiscipline of philosophy is going to have something to offer. Conversations that either have been taking place related to space topics or that need to take place. And I'm not saying every philosopher should just give up what they're doing and come do space stuff, but I'm saying if you're a philosopher and you're interested in issues related to space exploration, there is very, very likely something there and interesting and rewarding for you to work on. And I'm going to try to give some kind of preview of what my perspective is on what are some questions of interest, especially to philosophers. But there are quite a few other philosophers that work on these topics. They might have other ideas. So just consider this one perspective among several. So what am I going to try to do in this talk? Well, I'm going to start by giving a fairly brief overview in history of these policies known as planetary protection policies. So I'm going to be a little cagey on what that means yet if you don't already know, because I want to set up a really dumb joke in the next slide. But once we go over what those policies are, what they're for, I want to take us on something of a grand tour of ethics. That is, what are the primary ethical questions that planetary protection raises? What's some of the territory where people have explored responses? But that's mostly just some tour guiding there. And once we kind of finish that grand tour, as it were, I want to bring us back to considerations related to science. And I want to see how far thinking seriously about space science can get us when it comes to things like what we call planetary protection, or what's becoming more in vogue, things related to environmental protection in space. I think a deep understanding of space science is going to be absolutely vital for resolving some of the questions on the horizon. So this talk nominally is about planetary protection, and just to maybe get rid of some misapprehensions about what this might be, if you were imagining something like you see in this picture, let me just tell you that that is not in the job description of NASA's Planetary Protection Officer. That is a real job title, by the way. This looks more like planetary defense to me, but planetary defense generally refers to protecting Earth from asteroid collisions. Planetary protection is something different, but if that alien you see in the background is really, really, really tiny, and instead of being on some foreign planet that's trying to destroy Earth, it was on a spacecraft launched from Earth trying to search for some kind of life elsewhere, then picture might be accurate if you go with that metaphor. But planetary protection really looks more like what we see in these images. We've got these sort of vessels that are containing vehicles that are going to be sent to other worlds, and there's an attempt to clean them, not just to sort of make sure it's clean for the proper functioning of the hardware, but because if you send up things that might be contaminated with terrestrial organisms, and what you're doing is looking for life, if you're not careful to sort of be aware of what you're sending up there, there could be issues that could lead to unnecessary ambiguities and any potential discoveries you might make while you're looking for life or evidence of life. So if we want to get into the nature of planetary protection, and now I'm realizing I do not have a way to both see faces and read my slides, so I will have to make do with a little less reaction information. But anyway, sorry, I can see my slides. So what's the motivation here? I mean, what's going on with planetary protection as a policy measure? Well, the rationale, the justification ultimately comes from thinking about the science. And so in the preamble to the COSPAR planetary protection policy, it'll cite the justification for these policies as this, that the conduct of scientific investigations of possible extraterrestrial life forms, precursors, and remnants must not be jeopardized. In addition, the Earth must be protected from the potential hazard carried by a spacecraft returning from an interplanetary mission. Therefore, for certain space mission target planet combinations, controls on contamination shall be imposed in accordance with the issuances implementing this policy. So in essence, there are these sort of concerns about protecting scientific interests for certain kinds of investigations and also protecting Earth from potential biohazards from space, for instance. And I'm not going to get into the details of these policies at all because I want to talk more about sort of scope and justification behind them. But basically, the thought is, depends on where you want to go in the solar system, what kind of investigation you want to do. Are you just going to fly by a planet? Are you going to orbit around it? Are you going to land on it? If you land on it, are you going to go to any places that are very interesting in the search of life?
Exactly how I can help them in this project, mostly because with my limited skills in R and my lack of understanding of the different.
Okay. All right. So the actual measures that are recommended are going to be sensitive to what kind of mission that you're planning to send out, where it's going to go, et cetera, et cetera. Anywhere from just documentation to really extensive bioburden reduction and possibly sterilization measures, depending on exactly what you're trying to investigate. So the policies don't sort of apply to the same degree to every possible mission. But I guess what I'd like to observe here is that this is actually one of the oldest space policy tools out there. And the need for it was recognized all the way back in the 1950s in the build-up to the International Geophysical Year, which of course was witnessed at the launch of Sputnik 1. There were biologists, contemplating this new discipline, exobiology, which we now call astrobiology. And it was recognized that, if we might end up discovering life somewhere, we need to make sure that we're not going to be generating false positives due to terrestrial contamination. And then there might be concerns about introducing extraterrestrial matter to Earth, kind of outlined in novels like Andromeda Strain. And so in the sort of early 60s, by 1964, the Committee on Space Research, COSPAR, crafts and ever since has maintained a set of planetary protection policies. They get updated and evolve over time as we learn more things about the environments we're looking to study and as we learn more about our technical capabilities. But actually, so this planetary protection stuff kind of predates international space law. And we see that the planetary protection policies end up influencing what goes into the text of the Outer Space Treaty. In Article 9 in particular talks about prohibition on harmful contamination. And while a lot of people would like the legal definition of harmful contamination to refer to what's outlined in planetary protection policies, that is not something that the Outer Space Treaty requires legally, and lawyers would delight in interpreting it to their clients' benefit. But this planetary protection stuff has been a going scientific concern for a very long time, really as long as there's been space science conducted in space. And there are two basic issues here. There's protection against forward contamination and protection of Earth against back contamination. And for the remainder of this talk, I'm just going to focus on the forward contamination issue, in part because I think it's the more philosophically engaging one, but we're maybe not too far away from having to deal with this question about the Mars samples that Perseverance is supposed to collect and leave for a later mission to maybe return to Earth. we maybe need to think about bat contamination more seriously than we've been doing so far, but that is not something we'll get into in this talk. So from this point forward, when I say planetary protection, please just assume I mean protection against forward contamination. And in essence, it's a solution to a scientific problem. How can we be sure that any discoveries of extraterrestrial life or traces of past life are genuine and not false positives? And, over and above the kinds of considerations that I think Sean might have raised in his talk. I didn't get a chance to see it. I'm just assuming. But, how can we make sure that there's not unnecessary ambiguity in any discoveries associated with things about life on Mars, Europa, and Enceladus? But if what ultimately we're proposing is that we're going to have some kind of interaction with living organisms on another world, shouldn't there be some kind of ethical questions that we raise as we contemplate this endeavor? And, well, in this case, the scientists were the ones that kind of recognized this first. So go back in time to the mid-90s, we've got this exciting possible evidence of Martian life from looking at this meteorite fragment, I believe, I forget if it's an Antarctic or an Arctic meteorite fragment, but nevertheless, and it's not that little worm-like structure that's most interesting here, right? It's the magnetite. It's the mineral composition and thoughts about it would be easier to make if there were some biological processes that help produce it. But there's enough doubt that nobody really is willing to say nowadays that this is decisive evidence. But nevertheless, it looked really impending back in the mid-90s. And so all of a sudden, NASA's got to confront this idea that, well, if we discover life, we really haven't done any preparation for what happens after. So we need to start asking questions about, would it have rights? Is there anything related to morality? And so Mark Lupicello, who's a scientist that also has a background in philosophy, is one of the first to really directly ask questions like this, which, we must as a global society try to understand what position non-sentient extraterrestrial organisms will occupy in our ethical and political framework. Should primitive extraterrestrial organisms have rights of any kind? Perhaps the issue at hand is better understood in terms of value as opposed to rights. They'll certainly enjoy some degree of protection for scientific purposes, but is this the end of our worries? Well, there is a lot to unpack about how we might pursue answers to those kinds of questions. And so maybe we start by asking, well, what's the moral status of extraterrestrial life, especially if it's just microbial life? Because by and large, although we've got environmental ethics, which has extended things out to all kinds of life forms on Earth, there's been very little attention paid to the microbial world as a topic of ethical consideration. So maybe we can run one of the traditional kinds of anthropocentric or ratiocentric or sentientist views. And of course, those would probably imply that ET microbes are not sort of worth protecting for their own sake, but maybe if they were instrumentally valuable to other entities, that would be how they get involved in ethical obligations. But maybe there are other views out there, biocentric views, kind of like Paul Taylor's biocentrism, all kinds of ecocentric perspectives where you could craft a view around some kind of, example of extraterrestrial life or community of such life. And if you really want to push that totalizing direction, you can even think about sort of the whole cosmos, a cosmocentric perspective for thinking about ethics. And there are a couple folks that have tried to explore the implications of that. So there's a lot of sort of characteristically normative ethical work, meta-ethical work to consider on this question. And nearby questions of interest would be things like, well, look, if we're deciding to grant moral consideration to extraterrestrial microbes, would consistency demand some application of that principle back on Earth? And would that cause problems? Would that, be something we could fit into a coherent moral theory? And also thinking back in space, I mean, suppose we all agree and we've got a nice moral framework that implies there are obligations here to protect this life for its own sake even. There are other things people want to do on Mars, everywhere else in space. There are people that want to go and exploit resources. There are people that want to settle planets. And there might be incompatibilities here. We might not be able to satisfy all the obligations that we have. But ultimately, maybe you're not impressed by attempts to sort of assert that either microbes individually or as communities of life have some kind of intrinsic, final, inherent, whatever axiological term you prefer, value. So maybe you're not impressed by that. Maybe you think the odds of life existing are so low beyond Earth that it's not even worth thinking about. So we've got to grapple then with this question, well, what if Mars isn't home to life? And what if that's the case for the entire solar system? Would that mean we lose any kind of basis, especially a sort of ethical basis for thinking about protection of the space environment or aspects of it? And so I think a good place to turn for insight into questions like that would be environmental ethics, because there have been attempts to talk about the value of abiotic environments in environmental ethics. And here's just a very brief summary of a couple, I guess, seminal key papers, in my view, things that have had a pretty big impact. I don't want to say that these are the only works on the topic, and in fact, there's a lot in recent years. But really, space ethics kind of begins almost in the mid-'80s. There was a conference put on by environmental ethicists and scientists to talk about the terraforming question, and would it be permissible to remake Mars to be habitable for humans. And again, to the credit of the scientists involved, they were the ones that kind of reached out to, in this case, environmental ethicists for help as to, okay, we think we can do this, but should we? And Rolston writes this sort of beautiful overview of considerations that are relevant to think about. He's offering lots and lots of little different conceptual frames where we can look at a space environment and find something interesting there. And Rolston's telling us to, focus on what's there and what's interesting. Don't bemoan that you're not finding something you were hoping to find. So, don't be disappointed when Mars is lifeless. Be excited about all of the interesting things that there still are there. Alan Marshall, kind of reacting to some of that, is going to apply basic extensionist reasoning. So if we keep expanding the moral sphere, that's going to include the space environment eventually. Kikak Lee and Robert Sparrow, they both apply kind of virtue ethics perspectives to this question of terraforming. And then you can tell by the dates here, much more recent contribution comes from Tony Milligan, who is thinking about the notion of integrity. And there it's sort of claims like the integrity of X has been compromised. So Milligan is saying that's a productive way to talk about what damage, destruction, disruption might mean in a context where you've got geological features on other worlds, but they're not interacting with ecosystems or life forms. And so this is just a sketch of a very big part of some intellectual territory. So there's a lot to explore here, but maybe you don't want to get off the bus just yet. Maybe you think this is not the most interesting stop for your own consideration. So if you stay on that bus, or at least if you stay on the bus that I've been driving this talk, we're going to get back to science. And so I want to sort of revisit this original justification for planetary protection. And of course, the concern here is ultimately about protecting science, and in particular about protecting sites of interest to the search for life. So it's really about protecting certain investigations in astrobiology. And I would say that if we think we're justified in actually implementing these policies, and I would say that we are, well, that would seem to assume that the investigations they protect are themselves worth pursuing in the first place. And I kind of want to assume both of those things for the remainder of the talk, but see my book, The Value of Science and Space Exploration, for an attempt to defend it. So here is my starting point for thinking about, is there a need to protect other worlds beyond reasons of interest to astrobiology? And so Ivan Almar, who's an astronomer, has this to say, that if planetary explorers do not fully address the environmental consequences of their activity and do not protect the pristine surface of celestial bodies, all in situ evidence on the origin and evolution of planets, asteroids, and satellites will be denied to future generations of astronomers. Almar is saying, look at the potential cost to all kinds of science if we are not careful with the very fragile environments that we're interacting with in space. And I didn't have a copy of the paper to pull a quote from for this talk, but I really wanted to find something from the Matthews-McMahon paper on exogeoconservation. That's a wonderful paper. It's from your previous speaker. I would strongly encourage you to take a look at that if this sort of issue sounds interesting to you. Because they're giving some concrete advice about what kinds of things you ought to protect in order to preserve using certain kinds of methods of planetary science into the future. So I think the broader point here is that something like the contamination threat is by no means limited to astrobiology, and in particular, the search for evidence of life or traces of past life. Things like planetary science, which is a sort of more general conception of space science that astrobiology sits within it, but it still stands in contrast to things like astronomy, astrophysics. So planetary science seems like it would benefit from policies created to protect sites of interest to planetary scientists. And I think the underlying point here is really that scientific investigation just can always be conducted more effectively in pristine environments. And can we, increase the amount of environments that we keep pristine for that purpose? It's another way of understanding what I am sort of trying to promulgate. So I think a case study would help us maybe see the significance of some of the things I've been talking about. And we're going to turn to a really close by source for that case study, in particular the moon, because while Mars, Europa, and Enceladus, while those places are going to be really fascinating in the search for life, they're fascinating for all kinds of other reasons independent of the search for life. And the solar system is just chock full of really, really interesting places that we don't know very much about. And while we know a lot more about the moon than most other places in the solar system, compared to Earth, we barely know anything about the moon. So even on the moon, there's tons of science to do that we have not done yet. And if you want to get a sense of what some of the existing lunar science goals are, you can kind of look to the work of the different space exploration analysis groups and the lunar exploration analysis group, and their most recent version of the lunar exploration roadmap identifies these major science goals. That studying the moon can help us understand the formation, evolution, and current state of the moon. So where did the moon come from? It's been geologically inactive for quite a long time, so it's kind of a snapshot of a much earlier period, which will allow us to study its history more effectively than if it was a world with a lot of active surface recycling mechanisms. We can use the moon as a witness plate for solar system evolution. That cratering record all over the surface, that bombardment history can tell us about what was happening in the solar system over the course of billions of years. And the moon is also a wonderful laboratory. So there are going to be great places where you can install observing platforms that get rid of all kinds of interference problems, atmospheric interference, radio astronomy on the far side. You're shielded from Earth's radio emissions. And moreover, you've got this lower gravity environment where the atmosphere is virtually non-existent. And so you've got these different conditions where you can, run experiments and see how are things different compared to moon on Earth. And, we've got another data point where we can do some more interpolation and extrapolation from. And here's the thing, even that lunar exploration roadmap is not limited to outlining scientific considerations. It also identifies other important goals of lunar exploration, including maximizing commercial activity. There are a lot of resources on the moon that we might want to exploit for profit, for instance. Enabling and supporting collaborative expansion of science and exploration. So not only do we want to grow the science on the moon, but think longer term, more forward about human inhabitation of the moon. And there are all kinds of defense interests in space and on the moon, so security and defense purposes are there. So there's a lot of actors interested in lunar exploration. It's not just scientists. But now let's think about the moon for a moment. I've got images here on the left of the near side and on the right of the far side. And there are important differences between these that are very relevant for thinking about how the moon will be used in the future. So on the near side, you're seeing those darker mare regions. Those are going to be flatter terrain, And those are going to be some of the regions where that helium-3 is deposited from the solar wind, and those will be slightly higher concentrations than elsewhere. But we see cratering all over the place. So if you're thinking about very large structures, for instance, if you want to build a really, really big radio astronomy observing platform, talking about tens, if not 100 kilometers in terms of area, pretty limited places you can do it on the far side where you're shielded from radio emissions. So what I really just want to give you the impression of is, if you want to go to the moon and you have some idea of what you want to do, it's not enough just to go to the moon. You have to go to a particular place on the moon. Right? It's a very differentiated body, despite how homogeneous it might look. Right? The sort of, especially on the resource angle, concentrations are very differentiated. And so as others are observing, and this is a very recent paper from Martin Elvis, Alana Krolakowski, and Tony Milligan, and anytime those three get together, it's something that's very much worth reading. But they'll tell us this, that the sites on the moon likely to attract the most attention for future missions are confined to a number of areas on scales of mere kilometers. And these account for just a tiny fraction of the moon's total surface area of 38 million square kilometers. That's like 1 to 1.3 times the land area of the North American continent. And two of the sort of locations or types of locations they identify as particularly attractive sort of lunar real estate would be things known as the peaks of eternal light. These would be crater rims in the north and south poles that stand out compared to the other terrain and are always or nearly always exposed to sunlight, except when there's a full eclipse. And then often very close by, cold traps or permanently shadowed regions. So these are going to be sort of areas in the basins of some of these polar craters where they're always shielded from sunlight. And those are places where we know, in a couple of them at least, there's some water ice, and there could be as many as, I don't know, there have been some recent work that I haven't had a chance to look at, but estimates in the territory of, like, I don't know, 8 to 20 trillion kilograms of water. So, a middle, if you want to put that into a different kind of context, somewhere around 3 cubic kilometers of water, which can sound like a lot, but compare it to an ordinary lake on Earth, it's not very much. And so to give you an even deeper sort of picture of what we're talking about with these peaks of eternal light and these cold traps. The details on these are going to be kind of hard to see, and that almost helps prove the point. But on these images here, you see the lunar north and south poles, both below and above the 88th parallel. And so the diameter on each of these is around 120 kilometers end to end. So those dark blue areas, those are going to be those sort of permanently shadowed regions where there could be concentrations of water ice. And more difficult to see will be the light blue, the green, and the red regions. And those are going to be the higher illumination areas. And, well, you should be able to make out a fair bit of the light blue. You'll be able to see some of the green. If you're having trouble finding any of those red dots, it's because there's only like 4 or 5 of them. So the amount of areas in these really high illumination conditions are quite small. But I mean, think about on that south pole where you see right near the sort of very center of the pole, you've got that dark shaded crater, and then you've got like basically the entire rim is a high illumination area. Those rims are going to be great for solar power stations, right? You've got this uninterrupted access to sunlight, but also that's uninterrupted access to observations of the sun. So heliophysics studies can be conducted there, and we're going to have competitions of use. And of course, you're right by a water source that everyone is going to need for provisionings for human crew. A lot of people want to create rocket fuel by electrolysis and cracking it open into oxygen and hydrogen, and you can combine those for useful rocket fuel. So a lot of the activity that's going to take place on the moon is really going to be centered in these pretty small regions. And so I think we are just forced to grapple with really tough questions, and there's maybe not a lot of time to try to figure some of this stuff out, but we've got to ask questions like, how does the value of space science compare with the value of other kinds of activities we might engage in space, because there will be conflicts between them. We can't satisfy all of the obligations, or at least we can't pursue all of the goals that we'd like to pursue. So how, in general, how do we balance these competing interests, and how can that discussion be informed by a better understanding of the science that involved? And all the while, this is one of the most interesting things about working on space topics, which is you're kind of a bit unmoored from the precedent of Earth. You're working in a much bigger environment, and you have to be on the lookout for questioning more assumptions than you ordinarily would, because maybe we're projecting from limited data and some of the conclusions that are kind of universal for thinking about ethics on Earth and thinking about balancing interests on Earth. Some of the assumptions that we've made without realizing it maybe don't apply to the space case, and that's something that we need to check into more. But I think ultimately, if what we want to do, if you agree with me that we should protect sites of interest to more than just astrobiology, to kind of planetary science more generally, and on the moon or anywhere else, then I think we should also make a really good effort to try to understand planetary science and its methods. Because if we're going to try to create policies that are going to actually protect these places, that are going to be effective, they're going to have to be sensitive to how it is that planetary scientists engage in their investigations, right? We need to understand the methodology and the practice of planetary science if we're going to craft a meaningful and viable protection policy. And that's even before we try to fight battles associated with, economic, political feasibility. But we need to ask questions like, well, how is it that planetary scientists pick out research goals and promising hypotheses for investigations? And what are the constraints under which they operate in terms of selecting mission destinations? What are the different kinds of observing techniques that are used, and what assumptions are involved? And there's a lot of remote sensing used in planetary science. How is ground truthing in planetary science different from sort of ordinary geological ground truthing? If we're thinking about, a competitive environment where there are other non-scientific actors, we need to think about what are the sort of most urgent inquiries, not simply in terms of what the scientists are most interested in at any given time, but what's possible right now versus what's not possible once, say, Elon Musk gets to Mars. But even more fundamentally, we need to explore, how is it that planetary science relates to other sciences? Is it more akin to the geosciences, or is it more akin to astronomy or astrophysics? I suspect each analogy is going to reveal something interesting about planetary science, but neither is going to sort of cover it all. So there are questions about sort of the organization and authority of the sciences that we need to consider in the context of planetary science, and of course astrobiology and others as well. I knew I wanted to use this quote for a transition. I remembered the quote, but I didn't remember who wrote it. And it turned out it was Mark Lucasella again, and also from 1997 again. So some of these moves have been anticipated, just not developed. So what Mark Lucasella and John Logsdon have to say is that there's more than science that we've got to be concerned about, right? So looking further ahead, we might also wish to consider how we'll guide our actions when the scientific novelty wears off. So I'm making this big fuss about protection for the purpose of science, but that sounds like it might be a temporary thing that's just going to fade away in relevance, after a little bit of time. And I'm not that skeptical on this point. So I think the scientific novelty isn't going to wear off for a long time. I think there's still so much to learn about the moon that's not a running concern. But even if it does, just because lunar science sort of starts to lose interest, there's still everywhere else in the solar system. So, there's going to be this kind of shifting line in terms of, all right, we're happy enough with what we've learned so far. We don't mind if settlers and exploiters come and start to affect this environment, because we've learned the things we had to learn first, but maybe now we need to reset and have a different conversation about Mars, and then a different conversation about the Galilean moons, and so on and so forth. And look, even if I'm wrong about the importance of space science, that doesn't negate the importance of all the other kinds of ethical questions that we should ask, and there are way more than I've had time to mention. So if I've convinced you to get interested in this stuff, there are a couple places you might consider looking. I won't say too much about SOCIA, the Society for Social and Conceptual Issues in Astrobiology, because the president of that organization is going to be speaking to you in a few weeks, Kelly Smith. So Kelly, I believe, would be happy to tell you more there. I recently created a sort of virtual working group called Swig, the Space and Society Virtual Working Group. This is very much just a small forum for folks to sort of give talks to a small audience of specialists on works in progress. So it's a way of, maybe meeting some of the mainstays of this discussion, and it's a venue to try out new ideas. So if you want a safe place to, present a paper on space, consider Swig as a forum for that. And I just checked the website last night. I didn't have a chance to update it, but my email address does not appear there. And for reasons of not wanting more spam, I might not put it on there at all. But I would say just email me directly if you're interested in that group. I'm happy to share more information and add you to the mailing list. Thank you so much. I look forward to your questions.
Thank you very much, Jim. Thank you.